All right. Um, Thank you all for coming to this talk. What I would like to tell you today is what a modern mailman should know when he is going to deliver a message. All right. Well, I think most of us already know who I am, but let's go quickly over it. So my name is Rob Van Pamel, and I'm a developer at Access, working at the .NET League. I've been working as a developer since 2007, and since this year, I'm able to call myself an AWS community builder as well, something which I am proud on. And since 2007, I started to work in console applications, then working with WinForms applications, and then moved on to web applications, and then more and more towards the cloud till today. You will see that my presentation has a little focus on AWS. AWS is one of my most favorite cloud providers because of my background, where I had a greenfield project where I was able to select a cloud at a certain point. And at that moment, being a .NET developer, I had a very open vision, and we were able to select AWS as our cloud providers. Still something where I'm 100% behind. But now we are here to talk about asynchronous communication and synchronous communication and how we could deliver a message. Well, back in the days when I was creating applications, I was creating applications in a synchronous style. Let's say that I was creating an application, a web shop, and I have heard about service-oriented architecture, so I was creating two different services. The first one being over here, the checkout service, and then another service that I created, the invoice service. Now, what did I do at that moment? Well, I would create a method that was going to call the invoice service in a very direct way. He was going to say, well, now just create a new invoice. And it was working fine at the beginning. But what happened in reality is that more and more services are going to be added to your project. You're going to add, for example, over here, you're going to add a shipping service, or even a contact service. And at that moment, you will see that, well, that checkout service is gaining more and more responsibilities. And not only the checkout service on itself, but also the team who is going to deliver or who is going to create that checkout service is gaining more and more responsibilities. Well, because if the shipping service, for example, is going to have a breaking change in their API, well, at that moment, it's up to the team of the checkout service to implement that breaking change. So they're gaining more responsibility as well, or more work, like you can say. Another downside of this approach is that if more services are going to be added to your project, well, he's going to have to call more services. Calling more services is going to introduce more latency as well. And you can already see that it's really coupled together as well. It's something that we do not like as a developer. So why are we then bothering with this synchronous communication style? Well, previously in the past, we were working with monolithic applications. At that moment, if you had to call another service, it was maybe one service that you had to call, so it was not a very big deal. But nowadays, we are working more and more service-oriented, so it starts to become a bottleneck at a certain point. Now, you can still say, well, I would like to keep working with REST or gRPC, and I will implement some retry mechanisms with poly, for example, so you have back-off and retries and circuit breakers and all that kind of stuff. Yeah, it can work at the beginning, but the problem will start when your application is going to start scaling. Because what happens at that moment is that the load of your application is going to increase, and your throughput needs to increase as well. And what you will see over here on the red line is the line of the synchronous communication. The green line is the asynchronous communication, is that at a given moment, the performance of your synchronous communication is going to drop. Now, why is this drop happening at that moment? Well, at that moment, what happens in your application is that for each call that your service is going to do to another service, he's going to allocate some memory in your application. It's a thread who is open over there, waiting for response for the other service was coming back. That thread takes some memory. The more threads you have, the more memory you have, but you only have a limited amount of memory on your service. So what happens at that moment? Well, your service collapses, and you can see, for example, one of the errors that you can get back is that I'm unable to connect to the remote host. The connection was refused. So this is what happens at that moment. Now, what is the solution for this? Well, this is decoupling our application. Well, I'm not rating or trying to have a very small introduction. So I would like to introduce you to say why you would be using or why you are using messaging at this moment. I hope the Menti will work today. Yesterday it was not working, so let's find out. Is it working, or? Because nothing is popping up. Okay. So background processing can be one of the things that you use for messaging. Reliability, CRUD events, error and retry handling, scalability, load distributions. Very nice. Now, we're moving back towards synchronous communication, asynchronous communication as well, is that a lot of things can go wrong as well. Now, what are the things that can go wrong if you're trying to implement all these kind of things? What you expect is, well, I can say, for example, that all of the things that you might say is they are going to fall back towards the fallacies of distributed computing. And there, Dr. Harvey has mentioned all that fallacies. What are those fallacies? That are all the assumptions that a developer can make when he's creating his application. For example, the first one is that the network is reliable. Well, if you as a developer are not including that a network error can happen in your service, well, at that moment, if it happens, it will happen. So at that moment, well, your application can start maybe to stall, to wait for the response. It's not going to come, so it has to wait on the timeout. So your application will kind of hang, and maybe it's too bad. You will even have to restart your application as well. Another one is that developers might think that the latency on their services is 0. Well, if you have your local environment and you have your multiple services running on your local computer, at that moment, the latency is approximately 0. But the moment that you're going to deploy your application towards your production environment, that services are really distributed across a network. And then at that moment, the latency is not 0 anymore. So, well, people might then start to add caching, other kind of stuff to make sure that something goes fast towards the disk. But the latency of the network is something that a lot of people forget. So be aware that latency, if you're deploying it towards the cloud or towards a network, it's not going to be 0. Next one is coming up when you're starting to scale your application, is that the bandwidth is infinite. If you look at the amount of data that people are transmitting to the wire nowadays, it has been growing exponentially. I think 10 years back, when we were transmitting 10 gigabytes of data over the wire, it was already a lot of data that we were transmitting. But nowadays, we're not talking about terabytes anymore. We are not talking about gigabytes anymore. We're talking about terabytes, maybe petabytes or exabytes. But if you compare this with the magnitude of difference that you have in the speed of the wire that you have, it hasn't grown that much. I mean, 10 years back, we already had Ethernet cables of 10 gigabyte or connections or network of 10 gigabytes. And now, yeah, you still have them. And if you have a good one, you have 100 gigabytes. If you compare this with the amount of data that has been growing, you can see that a problem can start to arise over there as well. Now, the other one is that a network is secure. Network is not secure nowadays. I think a lot of people already know that security is something very important, that they should be aware that if you're going to transmit something over the wire, that should be encrypted. So take care of that as well. Topology is changing on your network as well. So don't try to call another service based on an IP address, for example. Make sure that you have a name server between it. It can be a DNS, but it can be something that you write yourself as well, that somebody has to, that the service has to register itself with its current IP, for example, and then you call your name server to make sure that you are able to call that other service. And another one, which I find interesting, is that there is only one administrator. Previously, it was like that there was most of the time an administrator who know how the network was working, but nowadays we have multiple teams who are working on a product, and the knowledge is not at one person's head anymore, it's just distributed across multiple teams as well. So you'll have to contact multiple teams to know how something is working if something goes wrong in your application. What you see a lot when you're working with cloud providers is that the transport cost is zero. If you're going to transmit a lot of data into the cloud, or you're going to transmit data between different regions or different services, you don't have to pay for it. At least that is what they're mentioning. But in reality, you're paying for it as well, because if you're putting something on the wire, at that moment you will start to serialize it as well. That serialization is going to cost you CPU power. And for that CPU, yeah, you still have to pay. So they mention that you don't have to pay for it, but transport cost is not zero at all. And then the network is homogeneous. Well, if you're working with the .NET application and you're starting to serialize something, and another service which is on your network where you have to communicate with is not working with .NET, but maybe with Java, at that moment you can start to have some serialization issues because you're serializing with, for example, Newtonsoft for JSON. Another one is working with Java, and it might be all JSON, but there might be subtle changes between them, and those can cause errors as well. So working with distributed or synchronous communication and asynchronous communication still have some fallacies over there. Now, how can we resolve most of them is by making use of those event-driven or asynchronous-driven architectures. Well, an event is a change that has already happened in the past, so you're not able to change it anymore. It's something that happens asynchronously, and it will make it easier for you to decouple your services. Now, how will it decouple your services? Well, if you focus on the communication, you will see that we are reversing the flow. Previously, we had the checkout service who was calling the shipping service. Well, if you're going to introduce something like a service bus, at that moment you will start to inverse the flow in such a way that the responsibility is not to the checkout service anymore who has to call the shipping service. No, it is the shipping service or the invoice service at that moment who is responsible for subscribing to a given event. The checkout service just had to publish its message towards the cloud, and then the other services have the responsibility to subscribe to these events. So at that moment, you are introducing a decoupling into your services. You're just broadcasting at that moment. So before we move on, I would like to know which kind, and that was too fast, which kind of technologies that you are using for message communication. The first ones are there. We see Kafka coming up. We see Azure Service Bus and Service Bus, Event Hub, AMQ, AWS SQS, Rebus, Azure Service Bus. What else do we have? Event Hub. Mass Transit comes back as well. Well, I was hoping for a word cloud like this, and in my slide, it looks more like this, but I think it's rather the same, or it might look the same. We have a lot of technologies that are popping up at that moment. For example, we have Event Bridge and Service Bus, ACTP, MQTT, QoS, ActiveMQ, AMQP, all these kind of technologies. And if you're starting to work with asynchronous communications, it might be a little bit overwhelming as well, because do I have to know all of them before I can start with it? Well, let me try to explain some of them. The first one I would like to install are what I call more patterns and principles. The first one is quality of service. Well, quality of service, we're just trying to publish a message from one service to another service. There's not a lot of quality of service. No? Well, actually there is, because we would like to send this message or deliver this message exactly once. Suppose that you will have to withdraw 10 euro from your bank account. You only want to have that this happens once. Well, in reality, it seems that this is not very easy. And there is something similar, which is called as the problem of two generals, where I can explain this exactly once quality of service with. Suppose that you are the general of, you have over here a red army, which is divided into two different values, and there are some mountains in between. And there is a blue army over there. Well, the generals of the red army have to start to fight against the blue army at the same time, but they are separated between by two different mountains. Now, how can they communicate to each other that they have to start to attack at the same moment? If they're going to send out a soldier towards A2 to say, well, we have to start at 12 o'clock this evening, at that moment we can attack, well, they have to pass through the value of army B, or the blue army, and at that moment they can get killed or conquered or whatever. So sending a soldier over there is not very easy. Let's say that it is possible for a soldier to get past. Now, the army A2 will know that they will have to attack, but how can the general over here know that the soldier has delivered the message? He has to come back and say, okay, I have delivered it. But at the same way, he has to pass again through that value of the blue army, and he can get killed again. So it seems that delivering a message exactly once is not possible if there is something unreliable in between. And this is why we will start to talk about at least once delivery and at most once delivery. At most once is more like a fire and a forget. I will not discuss this today, but I will focus more on at least once delivery. Now, before we move towards at least once delivery, I would like to introduce the idempotency concept. Now, what is the idempotency concept? The idempotency concept is, like you can see it over here, like you can read as well, is the property of certain operations in mathematics and computer science that can be applied multiple times without changing the result beyond the initial application. What does it mean? If a message gets delivered one time or two times, the outcome or the result will be the same. So it doesn't matter if it's delivered multiple times. So at least once delivery. Now, how can you achieve this? You can achieve this by adding a unique message identifier to your messages. And what will you do with this unique message? Well, you will store it inside your database. You will see over here that I have separated my database into an internal state and to an external state. The internal state is all the business logic and all the entities and aggregates that we like to store. And the external state is about all the messages that are happening outside of your application. Let's say that a message arrives into your service. What do you have to do at that moment is, well, you have to start to process it, of course. But you have the message ID over there, so you already store it. And then you start to your business logic. And maybe some messages have to be sent out because of the business logic that you have executed. Well, if some messages have been need to be sent out, at that moment you can store them inside that same table with that message ID. So you have the message ID over there, and you have the outgoing messages that need to be sent out. Well, let's say that at that moment the same message gets received again. What do you have to do at that moment? Well, at that moment you know, you can look it up into your table, you see message ID. Well, I have already processed it, so I don't have to process it again, so I can discard it. What do you have to do with those outgoing messages? Well, those outgoing messages, you still have to send those out, because you don't know if another service has already received those. But those other services will process it then twice. Well, no, if they follow the same principle, they will store the message ID as well, and they will know as well that, okay, I have already received this message, so I will not process it twice. So this is how you can receive that at least once processing at your receiver side. Now we still have another side as well, which is the sender side. How can we be sure that if you're going to process some business logic, that our message is going to be sent out as well? We need to be sure that it can be received, but we need to be sure that we can publish it on the wire, or we can publish it towards the other services as well. How can we do that? Well, for that, I would like to introduce that outbox principle. Now, what is this outbox principle? The outbox principle will try to separate, again, the two different responsibilities. You have the responsibility to process your business logic, and you have a responsibility to send out messages. Now, let's assume that we have a service who needs to process some business logic, and as a result of processing the business logic, he has to send out a message. Now, what will that outbox principle do? Well, instead of sending out the message directly, we will not send it out directly, we will store it inside a separate table. Like you can see over here, we have a table where you have some messages inside which contain an identifier, the event type, the moment they need to be sent out, and a very important one, aside from the payload, is has it already been sent or not? So this gives you the flexibility or the ability, if you're going to process your business logic and you commit your local transaction, that you can commit your messages inside the same transaction. Now, how can these messages then be sent out? Well, we will introduce another piece, is called the outbox, or an outbox processor. And what will this do? This will look at the table over there and look at all the messages which haven't been sent out. The messages that haven't been sent out will be sent out by that outbox processor. So instead of the service who is going to send out the message, it's now the responsibility of the outbox processor who is going to send out the messages. And at that moment, you're sure that if something is going to, if some business logic is going to be executed, that the correct messages need to be sent out as well. Now, we have focused on our service itself to be sure that all the transactions and all the messages are being sent out for that service. But how can we be sure, if we have multiple services in our application landscape, that we maintain the data integrity over there? This is where Sagas comes into the picture. Now, previously, and maybe some of you have known it as well, but in the past, you had something which was called a distributed transaction. Now, what was this distributed transaction? It was a transaction that would span multiple databases. So you would commit something to your database, and you would wait for another database to commit something, and at that moment, then the real commit is happening, and then it's being written towards the databases. The problem with this is that it doesn't scale at all. It just is slow, and if you're working nowadays with microservices which need to scale and be fast, it's a solution that will not work. Now, if you want to maintain our integrity over our different services, a saga is something that you can introduce. Now, what is this saga? The saga is going to represent the state of your different services, and it's going to add a state machine. So if something's happened in your application, it will send out messages across multiple services. But if something goes wrong in one of those services, that state machine has the ability to send some compensating actions as well. So to make sure that everything has already been committed in your local transaction, but by executing those compensating actions, he can start to roll back those actions as well. So for example, if you look at AWS step functions, those are actually sagas, but then spread out for a serverless application. Now, if you look inside and Service Bus, for example, you can work with sagas. For example, over here, I've added an order saga who has been started with a start order event, and it's going to handle as well some complete order events to make sure that the order has been completed correctly. Now, what else do you have over here? You have to have a correlation ID for your saga. Over here, I'm using the order ID, and this makes sure that messages who are going to be processed, that they are correlated to the correct service, and that the correct order is going to be completed, and not another one which has nothing to do with that order. Now, let's move on. We have already discussed about the patterns and principles. What else of services or terms do we have over here? You see, and Service Bus, Rebus, Mass Transit, and Brighter, who are going to be discussed. I would like to call these application messaging frameworks. Now, what do the application messaging frameworks do? They add an abstraction layer to your messaging infrastructure. They're going to take care of all the transport details. Let's say that you're working with SQS, or you're working with that you're working with an RabbitMQ. Well, if you're making use of these kind of application messaging frameworks, you don't have to know all the details about it. That application messaging framework will take care of it. What else do? They take care of message handling as well. For example, if you're processing a message from a queue, after you have processed it, you would like that it's going to be deleted from your queue as well. Even if as long as you're processing, you would like to know that nobody else can see that message because you are processing it. Well, this is something that those application messaging frameworks will do for you. And it works very easy. For example, in Service Bus, if you would like to process an order completed event, you just have to subscribe, or you have to implement that I handle message interface with the order completed. And over here, you can already start working on your business logic. So you don't have to know the details about SQS or RabbitMQ or whatsoever. Now, what else do these frameworks do for you? Well, they take care of routing as well. Let's say that you have to send a message from service A to service B. Well, they're going to take care of making sure that it's delivered to service B. If you want to serialize your message, or you don't want it, but you have to, they are going to take care of it. But they also take care of, for example, exception management and retries or poison messages. Let's say, for example, that your message can get processed at a given moment because the database is not available. Well, you can say, for example, I'm going to immediately retry it once because I know something can go wrong in the network configuration. And if it doesn't process it again directly, I'm going to retry it 3 times, but with a longer delay. So at that moment, you have the flexibility to have those retries already in your application without a lot of logic that you will have to write yourself. Now, for example, and Service Bus, this application framework has support for multiple transports, like you can see over here, RabbitMQ, SQS, MSMQ. It also supports the patterns which I just discussed about owlbox, idempotency, sagas. But there is a downside, of course. It's a commercial license. So if your project or your customer doesn't want to pay for it, there are some solutions as well. The other solutions are, for example, mass transit. They also have support for multiple transports. For example, the Kafka is also supported, ActiveMQ, Azure Service Bus. Another one is Rebus. Rebus also has support for RabbitMQ, AmazonQ, SQS, Azure Service Bus. They also support owlbox sagas and idempotency. And the same thing applies for Brighter. Now let me show you how it works, because I can tell a lot of things, but maybe you don't believe me from just saying it. Can you see the screen? Is this readable in the back? Yes, okay. So what do we have over here? Created a small application where we have one event, a simple my demo event, which is implementing an iEvent interface, nothing fancy about that. Now what else do we have over here? I've created a publisher and a receiver, one for RabbitMQ, like you can see over here, and a publisher and a receiver for SQS. Now let us take a look at that publisher. Over here I'm, by the way, using nService Bus. And what do you have to do if you're using nService Bus? You will have to create an endpoint configuration. Now that endpoint configuration, you have to say, you have to give it a name, of course, for what the endpoint will be. And over here, I'm configuring the transport that you would like to use. In this example, I'm using RabbitMQ. And once everything has been configured, you can start your endpoint, or you can start maybe your queue or something like that. Now what else do we do over here? We will start to publish messages to that queue, and we're just going to wait. Now what do we have inside the receiver? Something very similar. We also have an endpoint configuration. We are using the same transport, of course, and we are starting the endpoint over here. What else do we have in the receiver? We also have an event handler. I created the event, and now I would like to process the event. Processing the event is a big word. I'm just going to write the message towards the console application. So let's see if this is going to work. So over here on the left, I have my sender, and on the right, I have my receiver. So for those who have noticed it, in the beginning of my application, I have already published a message. So if I'm going to publish it now, it should be received at the other side as well. So you can see I'm sending it, and on the other hand, it's going to be received. Now, I've told you that the nService Bus is going to abstract a lot of details for you, and you shouldn't care about the transport or not a lot. So let us take a look at how such a receiver and a publisher look like if you're using SQS. Now, if you're using SQS, you will have to start with the same endpoint configuration like you can see over here. The transport, of course, this is going to differ a little bit because you're not using RabbitMQ anymore, so you have a little bit more details about the SQS transport. But you're using some serialization over here, and you're using that transport. On the other hand, what else do we have over here? We will have to start our endpoint over here. Over here, I'm publishing the same message, the same way I did before. And if you're looking at the receiver, it will look very similar to the one on RabbitMQ, where I'm starting an endpoint configuration, configuring the transport again, using the same serialization, and on the end, starting the endpoint. I also have my demo event handler over here, where I'm receiving the message as well. So you see that the similarities between two different transports using and service bus are very high. Now, let me first run it. So a message has been delivered to the receiver, or should have been delivered to the receiver. And you can see over here that it's already working. So it's receiving at that side. And if I close it over here, it's going to publish the message. It doesn't fail. The service is not available on the other side, but it still works. Now, where is the message? Well, the message is on my queue. Well, and if so over here, by the way, I'm logged into the AWS console. I am on my receiver side from my queue, and over here, I'm going to start polling for some messages, and it seems that I'm logged out. So I will have to log in again. Just give me a second. So normally there should be one message over here, and this is the message that I just sent. Now if you look at the details, a lot of the things which I just discussed come back over here as well. So for example, you have the service bus message ID, which is used for item potency, is stored over here as well. And some other stuff is over there, conversation ID, correlation ID, which is then, or can be used for example, sagas. And over here you have the body. You can see that some serialization has happened, and here the base 64 has been used. So if I'm going towards my scratchpad and, oops, base 64 decoded, you can see that my second test is the message that is on the queue. Now let's move on towards the next parts. Okay. So the next parts are about an event bridge, an Amazon SQS, a RabbitQ, Amazon MQ, Amazon SNS, ActiveMQ. And before moving into the details of all these transports, I would like to phase something out, because sometimes I feel it's difficult to create a difference between what is called a broker and what is called a bus. When I hear a broker, I'm always thinking about a centralized messaging system. You have, for example, a cluster where your messages are going to be stored, where all your queues are going to be stored. Such a broker can listen to multiple sources. It can listen to the different queues or to the different sources, yes. And what is important over here is that it has the ability to route from itself. So the broker knows if a message is going to be received for service A and it needs to be sent to service D. It's the broker who can do it on itself. On the other hand, a broker, in my words, are always on systems. So you're going to deploy a queue, a broker, and you can cluster it. But for high availability, you need to maybe deploy 2 or something like that. On the other hand, you have a bus. And a bus, in my eyes, are more distributed systems. You have more different queues, which are not correlated to each other. And they have more a shared message, agreed upon a set of a message schema. On the other hand, you have the principle of smart endpoint and dumb pipes. So all the logic is not inside your system itself. It are the endpoints who are responsible for sending a message to the other service, where in a broker the knowledge is over there. For example, if you're using application frameworks, they are going to take care of that knowledge of routing, for example. And most of the time, the buses are serverless. Now, what do we have for brokers is, for example, an Amazon MQ. What is an Amazon MQ? An Amazon MQ is a managed service from AWS for broker systems like a RabbitMQ or an ActiveMQ. Now, what is a RabbitMQ? A RabbitMQ is most of the time a managed service for the AMQP protocol. You can have different protocols on it as well. It can support Stomp, for example, as well. But most of the times it's running on AMQP, where you have multiple scenarios available. For example, you can do the publish-subscribe mechanism, you can have routing, but you can also have request-reply style of message sending. Then you have on the Amazon MQ also the ActiveMQ. ActiveMQ is also a broker like I just mentioned, but it's, in my eyes, more for the Java people over here in the room, because it has more support for Java than it has for .NET. And most of these systems also support clusters. Now, on the other hand, we have the bus systems, and the bus systems we have in AWS are SQS and SNS. What is SNS? SNS is the simple notification system where you have a publish and subscribe mechanism, where you can have different endpoints, and one of those endpoints can be an SQS, and an SQS is then a queue where you can store your messages on. It's also a managed service of AWS, and most of the times they are used in combination. For example, if you're using Service Bus in combination with SQS, they're mentioning SQS, but behind the scenes they're also using SNS. One thing important or funny to notice as well is that on SQS you can have FIFO queues as well. And with FIFO queues, they are mentioning that they can have that exactly once processing, which I just discussed, which was impossible. They're claiming that they can have it, but if you're going to read into the smaller letters, you will see that it's only valid for 5 times. So what are they going to do? They're going to store your message ID for 5 minutes, and afterwards they are going to discard it. So if your message arrives after 6 minutes, you will still have that double processing of your message. Now, what else do we have? Amazon Event Bridge. Amazon Event Bridge is more a serverless bus system, which was built on top of the CloudWatch events. It consists out of different pipelines. You have pipelines for, you have a default pipeline, which is used by the AWS events. Your own events can be placed on your custom pipeline, or you can have partner events. For example, if you have a Jira or Confluence and you would like to publish something from Jira or Confluence on your pipeline, you can use that partner pipeline for it. They have support for multiple events, which is kind of logic, and you have multiple sources and targets. Targets can be anything, sources can be anything as well, as long as you can interact with it. You can apply different rules. For example, let's say that you would like to send a message just between 10 and 11 if it arrives. Is something that you can configure inside the rule. And which is another thing which is nice to have is that they have an event schema. An event schema where you can add all your messages inside, and then you can have one source of truth where the schema of your events is described. Now, what else do we have? You see that the list is going to get a little bit smaller, is HTTP, MQTT, MSMQ, and AMQP. Now, these are the protocols which are used behind the transports as well. Now, the first one I've already discussed is AMQP. AMQP is being built by the Bank of America, and it's being built for purely enterprise systems or building enterprise systems. It's using a binary protocol, and the support for multiple scenarios is the same, for example, like a RabbitMQ. Now, the other one is HTTP, maybe one that you don't expect over here, but for example, SQS and SNS are making use of HTTP to sending out messages to each other. This was not the initial purpose of HTTP, but they are still working on it. And in the past, they had some issues with delays. But by making use of the third version of HTTP, where some major improvements had been made for the performance, mainly on TLS, a lot of speed or latency is gained over there. It can make use of UDP, where previously in the past they were relying on TCP and even on QUIC, but be aware that some companies are still blocking UDP and QUIC, so it might not work the way you expect it to be. Now, what else do you have for transport or for protocol is the message queuing telemetry transport. You can already hear it, it's telemetry. It's being built for IoT devices to send data from the IoT device towards a broker. You hear it as well. They're going to send it to a broker, which means that it doesn't live on itself. It needs a broker, for example, AWS IoT, for making sure that messages are going to be routed towards the correct endpoint. And then, last one to discuss, and maybe one of the oldest, aside from HTTP then, is Microsoft Message Queue. And Microsoft Message Queue, I still like to mention it because maybe some projects are still working in .NET Framework, and then you can still make use of it. It already exists from Windows NT4. You can already guess how old it is. But it has support for those distributed transactions if you would still like to use it. I don't recommend it because it's been discontinued, but you can still have it. And one of the things which was nice about it is that it had the store and forward principle at that moment, which was the kind of an outbox that I just displayed, but back in the days it already existed. But maybe not in very good fashion, but it already existed at that moment. So if you're working with an old project, you can still use Amazon MQ. Microsoft Message Queue, sorry. Now, if we wrap up, you see that on the left, we discussed all the patterns. We had the sagas, the idempotency, quality of service, the outbox, and then we had the application messaging frameworks like an service bus, who is on its side then making use of some message transports like RabbitMQ, SQS, EventBridge, which is on their side then relying on the protocols like an AMQP, MQTT, and all the other protocols over there. So that was it for today. I would like to thank you very much for attending this session, and I hope you learned something today.